This is the third class on tensor algebra. In the earlier two classes, we have discussed tensor. Mainly, we have introduced covariant and contravariant vectors and explored some of their properties. And in the last class, I have also outlined a problem for the calculation of divergences of a covariant and contravariant vector when the transformation involves between Cartesian and the cylindrical coordinate system. As I have received some requests from a few bodies and I have been requested to work out the problem in detail. I think it would be helpful for the beginners to follow the step-by-step procedure for the calculation that was outlined in the first class, in the last class. So our objective is the divergences of covariant and contravariant vectors in cylindrical coordinate system. First of all, I want to mention that the transformation relation is x is equal to rho cos phi, y is equal to rho sin phi, and z is equal to z. The inverse transformation relation is rho is equal to x square plus y square square root tan of phi is equal to y by x and z is equal to z. So the partial derivatives that will be involved is del x del rho is equal to cos phi, del y del rho is equal to sin phi, and del z del rho is 0. I am not this is del z del rho is equal to 0. Then differentiation with respect to phi, del x del phi. If we differentiate this relation, we get 1 plus tan square phi del x is equal to minus y by x square. And for tan phi, I write 1 plus y square by x square del phi del x minus y by x square. So this is x square taken common, the numerator is del phi del x is equal to minus y by x square. That is del phi del x is equal to minus y by rho square, and if we put y is equal to rho sin phi, this is minus 1 by rho sin phi. So this is minus 1 upon rho sin phi. Similarly, del y. Sorry, I have this is the expression for del phi del x, and I am going to calculate del x del phi. Sorry, del x del phi. Del x del phi is equal to minus rho sin phi. Del y del phi is equal to rho cos phi, and del z del phi is 0. Del z del phi is equal to 0. Similarly, del x del z is equal to 0 is equal to del y del z, and del z is obviously y. The other relation is that del rho del x with del rho del x, if we write it, rho square is equal to x square plus y square. So rho del x is equal to x. So del rho del x is equal to x by rho. X is equal to rho cos theta. So this is simply cos phi. So this is cos phi. Del rho del y is equal to sin phi. Del phi del x that I have calculated earlier is minus 1 by rho sin phi. Similarly, del phi del y is equal to plus 1 by rho cos phi. These are the partial derivatives that will be of need in subsequent calculation. For the evaluation of the divergence, we will be in need of performing operation like del x, del such things. So del x can be written as del rho del x del rho plus del phi del x del phi plus del z del x del z. This is 0 as I have pointed out. Del rho del x is cos phi del rho. Del phi del x minus 1 by rho sin phi del phi. So we write del x is equal to cos phi del rho minus 1 by rho sin phi del phi. Similarly, del y is sin phi del rho plus 1 by rho cos phi del phi, and del z is equal to del z, because z is do not undergo any change. Now come to the definition of a covariant vector. The covariant vector is defined as a covariant vector AI is defined as del x bar alpha del xi a bar alpha. We consider the S prime we consider to be the xyz frame. The S prime is, and bar frame is we consider as rho phi z frame. So what we get? We get for ax I is equal to x, so this is del rho del x a rho plus del phi del x a phi plus del z del x a z. Now del rho del x is cos phi, so it is cos phi a rho plus del phi del x is minus minus 1 by rho sine phi fi. So the component of covariant vector is ax is equal to cos phi a rho minus 1 by rho sine phi fi. Similarly, ay, for calculation of ay, this x will be replaced by y and we will have, this is sine phi a rho plus 1 by rho cos phi a phi, and for z, this is z, this will be za, and only this term will survive, az is equal to z. So these are the components of covariant vectors. Now, the divergence of a covariant vector, is defined as divergence of AI is defined as del x plus del y plus del az del z. Now we first calculate this part. So del ax del x is equal to del x. For del x we write this one cos phi del rho minus 1 by rho sine phi del phi. This operates on ax. The ax expression for ax is this. So this is cos phi a rho minus 1 upon rho sine phi a phi. First, if we calculate this one, this is cos square phi del a rho del rho. When this operates on this, there are two operations. One is rho operating on this. This gives you minus 1 by rho square. So this makes it plus 1 by rho square cos phi sine phi a phi. And then this operates on this, which gives you minus 1 upon rho cos phi sine phi del a phi del rho. Now this part, when this operates on this, we get minus sine theta, so that altogether we have 1 by rho sine square phi a rho. Now then this operates on a phi. In that case we get minus 1 by rho cos phi sine phi del a rho del phi. This is the term that we get when this operator operates on this, and when this operator operates on this. Firstly, this is plus rho square, and this operates on this, so we get plus 1 by rho square. This will be cos phi, so this is cos phi sine phi a phi, and this, when this operates on this, we get plus 1 by rho square sine square phi del a phi del phi. If we work out similar calculation for what del a y del y, I am just indicating the change that will appear. This term will be called, this will be sine square phi del a rho del rho. This term will be, they will get cancelled. Just a minute. There are two terms, similar terms, so there will be a two factor. So we will have 2 by rho square cos phi sin phi a phi plus 1 by rho cos phi sin phi a phi a rho plus 1 by rho cos square phi a rho plus 1 by rho cos phi sin phi del a rho del phi. This term has already been adjusted, so this term plus 1 by rho square cos square phi del a phi del phi. So when we add, and there is a term del a z del z del z, which is del a z del z. So when we add the terms, there is a cos square sin square, this will be del a rho del rho, and this term cancels out, this term also cancels out, there will be 1 by rho a rho, and there is a contribution coming from this. So altogether, divergence of a covariant vector when expressed in cylindrical coordinate, there is a contribution del a rho del rho. Then we have contribution from this term plus 1 by rho a rho. Then there will be a contribution from this term 1 by rho square del a phi plus del a z del z. So this is the divergence of a covariant vector. So we write it divergence of a covariant vector when we express it in cylindrical coordinates. This becomes del a rho del rho plus 1 by rho a rho plus 1 by rho square del a phi plus del a z del z. Now I am going to calculate the divergence of a contravariant vector. Before going there into the calculation, first let me evaluate the components of contravariant vector, or the transformation of the contravariant components of a vector, where we transform ourselves from Cartesian to the cylindrical. Contravariant vector. contravariant vector, we know that they are defined like this. As usual, the S prime is our Cartesian from x, y, z, and bar from is our cylindrical from. So we have Ax, the contravariant component of it is del x del rho A rho plus del x del phi A phi plus del x del z A z. Obviously this part is 0, and del x del rho is cos phi, so this is cos phi A rho plus del x del phi del x del phi is minus rho sin phi minus rho sin phi A phi, and the z component is 0. So our definition of Ax is cos phi A rho minus rho sin phi A phi. If we calculate similarly the y component, it will be sin phi A rho plus rho cos phi A phi, and z remains unchanged in such transformation. Now the task is to calculate the divergence of the contravariant vector. So divergence of the contravariant vector is divergence AI is equal to del AX del x plus del AY del y plus del AZ del z. Let me first work out this one. Del AX del x. For del x, I write this one. This is del rho minus 1 by rho sin phi del phi. This operates on Ax, the x component of it is cos phi A rho minus rho sin phi A phi. Now, as usual, I have to perform this calculation. If you work out this one, this is cos square phi del A rho del rho. There is no more term when this operates on this. When this operates on this, first is when it operates on rho, this is minus cos phi sin phi A phi. And when it operates on this, we get minus rho cos phi minus rho cos phi sin phi del A phi del rho. Then this operation. When del phi operates on this is minus sign, so minus makes plus 1 by rho sine square phi a rho. Then this operates on this, gives you minus 1 by rho cos phi sine phi del a rho del phi. Then this operates on this. For firstly, when it operates on sine theta, this gives you cos theta, and there is rho cancellation, and the sign will be positive. So this is cos phi sine phi a phi, and when this operates on this, we will have sine square theta plus sine square theta, sorry, sine square phi del a phi del phi. For Ey, the changes are like this: del A del y. This part will be cosine. This will be cosine square. This will appear with plus sign. This will appear with plus sign. This will appear as cos square phi. This will appear with a plus sign. This will appear with a negative sign, and this will appear with a cos square phi. So if we write it explicitly, it is sine square phi. Oh, there is one more thing. This term will go. This is a plus sign, and this is with minus, and this goes. So we need not to consider that. It gets simplified. It gets simplified to cos square phi del a rho del phi, then minus rho cos phi sine phi del a phi del rho, then this term 1 by rho sine square phi, 1 by rho sine square phi a rho, plus with minus 1 by rho cos phi sine phi, this term del a rho del phi, and finally this term. So this will be, first thing, this is sine square. Then this will be our plus sign. Cos phi sine phi. This is plus 1 by rho cos square phi a rho. This is plus 1 by rho cos phi sine phi del a rho del phi plus cos square phi del a phi del phi, and phi del a z del z is equal to del a z del z. It remains unchanged. So when we add the term, this term and this term makes it del A rho del rho. We have considered these two terms. This term will get cancelled. Then we will have this term 1 by rho A rho. Then this term will be cancelled and this term will be del A phi del phi and finally the term coming from Z del AZ del Z. So I remove all these This is the final expression for the divergence of a contravariant vector when expressed in cylindrical coordinate system. So we see that there is a difference of the expression of divergence when evaluating even in cylindrical coordinate system. These two terms are similar, this is also similar, this is also similar, difference lies with this. If you recall that the divergence of a vector as we have calculated in vector analysis class, this was del A rho del rho plus 1 by rho, A rho, rather I write it as del rho of A rho. This is the rho component of the vector, not the function of rho. Then 1 by rho A rho. Then this part. A phi and finally del A Z del Z. We see that all the three expressions are different. These three terms are similar in all three expressions. Only thing that we need to consider that here the factor is 1 by rho square. In this case the factor is 1 and here the factor is 1 by rho. So these are the different expressions for the divergence when evaluated in cylindrical coordinate system. Similar calculation may be performed in spherical polar coordinates when we consider the expression for the divergences of a vector, covariant and contravariant vector in spherical polar coordinate system. I insist you to work it out at least once in a life. That's all for this class. In the next class we shall continue our discussion on the properties of covariant and contravariant vectors, and we shall give a physical explanation of the covariant and contravariant components of the vector, and finally we switch over to tensors of rank 2.